Does this one work? Yeah. This one works. Okay, awesome. So hi, everyone. My name is Keaton Ellis. The work that I'm going to be presenting to you guys is joint with Shahar Karif, who is in the econ department, and my advisor, Erkut Isbai, at the University of Maryland, where I come from. And I think unlike most people in this room, I am an economics PhD, and I definitely come from a very different space, but hopefully there's some things that you'll find interesting about this talk. I'm an experimental economist, which means in particular that unfortunately I have to deal with humans. So I don't have theoretical guarantees in the exact same way, because even if I prove some theorem about a theory model, it may not actually work on the people that I'm trying to analyze. So in particular with economics, economic theory in particular has this very sort of strong tie to experimental economics in the sense that, you can construct a theory, you can say it's a model if and only if you have some axioms on choice, but then you actually need to go and see whether or not people actually choose in that way, and that's where experimental economics comes in. Within this, there are a bunch of different ways that people care about experiments and run experiments on people, either in the lab, in the field, with lots of people, with very few people. I focus on lab experiments, and in particular, I focus on lab experiments where I look at a single individual's decisions. It may affect other people, but it's a single individual's decisions. And generally, the common theme in this type of work is that I have various decision theoretic models that I've got, and I want to go and distinguish between them. I've got model A that someone's proposed. I've got model B that someone's proposed, and I want to distinguish between them by cleverly constructing an experiment such that if I associate with model A, I choose X. If I'm more consistent with model B, I choose Y, and so on. I've got work in this. There are things that people do in this space, plenty. But generally, this analysis is done sort of relative to other economic models. So I have, two models that I care about that people have made very strong assumptions about choice. And whether or not these assumptions are correct are one thing. But one of the things that we were interested in doing in this project in general is sort of taking the concept of machine learning algorithms, where I don't have as many stringent assumptions about decision making, and it's more or less just some sort of function approximation to data. But it has very useful out-of-sample prediction properties, which is generally not what you think about when you think about sort of economic analysis. Maybe you think about consistency with some preference, or sort of how I can recover preferences from data that people have. But it's still a very useful question for applied demand analysis. And the typical approach that you're going to get is something along the lines of, I assume some model, I estimate some parameters associated with it, I have a demand function that I get from that model, and then I go fit this to some data that I care about. And one of the things that we're interested in checking is, instead of assuming I have model A and model B and try and test these, instead, under what empirical conditions do our models with very strong assumptions outperform more flexible models, and in this case, we're just going to use machine learning models for that. And so in this project, we compare the relative prediction accuracy and then also the model flexibility of economic models, in particular one that I'll talk about in a second, to machine learning models. And we're going to run what we think is a fair horse race here, where all models are going to receive identical input, and they're going to be asked to predict exactly the same thing. We're going to be doing this all at the individual level. And so we have about 1,000 people in the data set that I'm going to be talking about. We're going to, for each person, train a model and then have it go predict what that specific person is going to do. So we're not including any information across individuals. We don't have extra information like choice response time data or any sociodemographic information that would be feeding into a machine learning model. So we're just going to run it in that way. And then the thing that we're going to be using is budget line experimental data, which is sort of what classical microeconomic theory is built on. And so we're going to be able to use these classical revealed preference techniques in order to analyze our results. And we're going to be using 3 separate tools in order to try and analyze what we see. First is just a measure of prediction accuracy, where more or less what I do is I scale my results sort of from 0 to 1. Where 0 is I have, no benchmark improvement over, does this thing work? Oh, cool. I have no benchmark improvement over a random benchmark model that I have. And a completeness value of 1 is that I'm going to have the best possible prediction that I can in any specific environment. a similar measure for model flexibility, where I can talk about sort of how a model can fit any arbitrary data that I throw at it. If I have a restrictiveness value of 0 in this case, my model can more or less connect the dots to any data that I want. And if I have a restrictiveness value of 1, my model is going to be no more flexible than a benchmark, which again, I'm going to assume is just random uniform choice. And then finally, we have a measure of consistency with GARP and first order stochastic dominance, which are sort of axioms that underpin utility maximization. And that's a cardinal value, so I can say sort of whether or not someone is more consistent with these axioms and sort of how much more consistent they are. So for this experiment, we've got 956 subjects, and they face a budget line that looks like this. There are going to be 2 equally likely states of nature, states 1 and state 2. And what we've got is, got for the subjects is these x and y axes correspond to arrow securities associated with each state. And so an arrow security is going to pay out in the state that it's associated with, and it will pay nothing otherwise. And what we're going to be doing is just taking this type of question where, if I make some choice, my x-axis is going to be how much I get paid out in state 1. My y-axis is going to be how much I get paid out in state 2. I'm going to have subjects make a choice on this, and then I'm going to have them do that 49 more times. So I'm going to ask a subject to sort of make this decision where I vary these prices by essentially varying the slope. I can make it flatter. I can make it steeper. I can push it out. And the goal for our models is to predict just a one-dimensional output along this line. So, of course, this is going to be a sort of analysis of machine learning models versus economic models. Relative to some of the applications that you guys use, we have very small data sets. And in that sense, we're using very simple regressions, tree-based models, and very small neural networks in order to do our prediction on the machine learning side. And we're just going to be pulling things from the literature that have used these types of models before. In terms of the economic model that we're looking at, we're going to be using rank-dependent utility, which is a sort of a behavioral economic model that is an extension of very classical economic theory, where essentially what I have is I've got additive separability among the 2 states, and then the state that is sort of giving me a lower payoff, I'm going to be weighting that state by some parameter alpha. And if alpha equals 1, I'm in a very special case of expected utility, which is more or less the backbone of most economic analysis. This also satisfies monotonicity with respect to first order stochastic dominance. And like I said earlier, we're going to just assume some utility functions, and more or less we'll have 2 parameters based on whichever one of these I want to use. I'll have one parameter, either rho or gamma, and then I'll have an alpha parameter that I'm going to go estimate via data and do out-of-sample prediction on. And in terms of the initial results that we're going to be getting, higher completeness values are better in this case. So when we take a look at our rank-dependent utility model against any of the other models that we're taking a look at, it's at least as good as sort of each individual family of models that we're looking at, but it's worse than if I take sort of the ex post best model per subject. And when I take a look at the family of models that we're comparing against, despite the fact that sort of rank-dependent utility and tree-based models have more or less the same completeness, so they have more or less the same prediction accuracy, a rank-dependent utility is going to be more restrictive, which means it's less able to fit any data that's thrown at it. It's got stronger assumptions on what the functional form can be. I've also got results for expected utility. It's more or less exactly the same as rank-dependent utility, so that special case doesn't hinder out-of-sample prediction at all, and it's slightly more restrictive. So the literature on this generally wants, if I'm thinking about it from sort of driving an economic theory perspective, I want more completeness because I want a model that has better out-of-sample prediction. And then I want more restrictiveness because I want a model that whose assumptions that I'm making on it are the correct assumptions that describe behavior. And so it's sort of lexicographical. I want completeness first, and then after that, I want restrictiveness. I don't really care if I'm making, if I have very high restrictiveness, if the assumptions that I'm making are not actually correct. The other thing that we took a look at here is instead of just taking a look at subjects on average, what we did was we took subjects and we sort of binned them by how consistent they were with our axioms of economic choice. And these are sort of equally sized bins of about 250 subjects each. And the leftmost bin constitutes the subjects that are least consistent with rationality. The rightmost bin are the subjects that are most consistent. And then the y-axis here is the proportion of subjects for whom our model rank-dependent utility is going to be more complete than the various machine learning models that we're taking a look at. And the main thing that we're seeing here is that as I get more consistent with our axioms of economic choice, of utility maximization, the model that uses these assumptions does monotonically better. Although there do exist subjects, even at the top, for whom machine learning models that we're analyzing do better. And this is not necessarily driven by one model doing the same more or less across all subjects. I'm going to show a series of scatter plots here where instead of showing the relative performance of one model over another, instead I'm showing sort of the completeness value of each model per subject on the x and y axes. Where if I'm on the 45-degree line here, I'm going to be taking a look, I'm going to be having the exact same predictive accuracy for that subject, regardless of which model that I use. This is the first quartile, this lowest consistency with our axioms. And most subjects here are on the 45-degree line, although there are subjects who are in this sort of top half of our diagram here, where rank-dependent utility does fairly poorly, and machine learning models do fairly well at predicting them. These seem to be subjects that have systematic violations of the axioms in a way that are easily predictable by a machine learning model. Otherwise, most subjects are along this 45-degree line within some sort of band. And as I consider more consistent quartiles of subjects, what I essentially end up getting is sort of a shift towards this upper right corner. So it's not necessarily that machine learning models are doing bad, even on the most consistent subjects, but rather that there's just a slight nestling underneath this 45-degree line as I move up. So in terms of the sort of conclusions that we draw from this, at least right now, so long as the assumptions underpinning my economic models are moderately satisfied, in general, the economic model performance is going to be better. Hooray, I can toot my own horn as the economist in the room. There is a caveat, of course, which is that this more or less is probably the best data environment that you're possibly going to get for an economic model, in the sense that relative to other data sets that we have, at least in experimental economics, we have a lot of individual level data per person. There are no causality concerns because this is an experiment, and things are mostly going to be explained by risk and or loss aversion in this environment. Of course, the counterfactual that economists are particularly concerned about is, if this is the best environment and machine learning models were doing better than economic models just sort of straight off the bat, we should be very concerned. I probably would not have a job. The other thing that we're seeing is that, the measures that we're using to talk about consistency with our axioms tend to work. As I get more consistent subjects with respect to GARP and first-order stochastic dominance according to this measure, our models do better on those individuals. I mean, that's sort of a confirmation that these metrics actually do what they're supposed to do, or at least intuitively are supposed to do. And so the things that we're interested in looking at is whether or not sort of, this is too special of an environment. It's too good for this all to be true. In the sense that we're going to be taking a look at more complex choice environments for subjects, either environments where subjects are asked to do sort of harder problems by either considering more goods, I'm varying the probabilities, I don't even give them the probability information, things like that. And also potentially more complex environments for the models. So if I have multiple experiments of data that someone may have, if I'm giving models additional information about responses, sort of whether or not any of these things change. And that's all I've got for you guys. Thanks so much.
Thanks a lot. So we have time for one quick question, maybe while the next speaker sets up.
Could you explain the experiment that you did? So you have the line. Didn't understand exactly.
Yeah. So what the experiment is essentially this type of setup. Sorry, let me move this. I apologize. The experiment is going to be more or less this type of setup for 50 different questions that a subject is going to see. So the x-axis corresponds to a bundle of arrow securities for state 1. The y-axis corresponds to a bundle of arrow securities for state 2.
What do you mean by arrow security?
And an arrow security is an asset that will pay off 1 if the state associated with the arrow security is realized and 0 otherwise. And so I've got these two states of the world, 1 and 2, and sort of the x-axis corresponds to the arrow security for this first state, and the y-axis corresponds to the arrow security for the second state. And so how I can interpret any point along this line is that, if I'm at some arbitrary point, and if I select this, if state 1 is realized, the x-axis the x-coordinate is what I'm going to be paid. And if state 2 is realized, the y-axis is what I'm going to be paid. And we actually pay subjects the money based on the actual choices that they make. And they do this, we do this 50 times per subject.
Well, thanks a lot.